final talk. So next speaker is Kanato Goto from Riken, and he's going to tell us about replica wormholes for evaporating to the black hole. So please start.
Okay, let me thank organizers for giving me an opportunity to talk here. Today, I will talk about my recent work on the replica wormholes for an evaporating 2D black hole. Okay, so let me start with the introduction of black hole information paradox. As we already know, the thermodynamic nature of the quantum black hole is one of the most fascinating and mysterious things in gravity. As Hawking pointed out, the black hole behaves like a thermodynamic object that has a temperature and entropy given by the area of its horizon. And as an ordinary thermodynamic object, black hole thermally radiates, which is so-called Hawking radiation. This leads to a well-known problem, so-called black hole information paradox. I will explain it briefly. On the right-hand side, I plot the time dependence of the entropy of the radiation. Hawking's calculation of the entropy of the radiation tells us that as time evolves, the entropy of the radiation is totally thermal, and as time evolves, more and more Hawking radiation comes out from the black hole, so its entropy just goes up until the black hole is fully evaporated. But this contradicts with the unitarity of the quantum mechanics, since if we start with the black hole in a pure state, the radiation should always be purified by its complement, that is degrees of freedom of the black hole. However, what the black hole entropy formula tells us that as time evolves, since the area of the black hole horizon gets smaller by the evaporation, the degrees of freedom inside the black hole is just going down. So at late time, black hole becomes too small to purify the Hawking radiation, and the total state becomes truly thermal. But this can never happen in the unitary quantum mechanics. Unitary time evolution indicates that this curve should start to decrease at time, so-called page time, and this unitary curve is so-called page curve. The problem is why the Hawking's calculation was wrong and how we can get the unitary page curve. In recent papers by Alan Haley, Engelhardt, Maroff, and Maxfield, AMM in short, analyzed the time evolution of the entropy of the radiation in an evaporating black hole in the ADS spacetime coupled to a bath system. On the left, I draw Penrose diagram of the system they analyzed in their papers. In the green region is a gravitational region where the gravity coupled to a metal CFT lives. And the white region is the bath system coupled to ADS2, where the same CFT lives, but there's no gravitational degrees of freedom, and we have a rigid flat spacetime. If an evaporating black hole exists in the gravity region, it emits the Hawking radiation. And since we have attached the flat space to the ADS region, the radiation can escape into the flat white bath region on the right. Then, if we place the region R here at some time t on the white region, this region can collect the Hawking radiation, which escaped before the time t. So by computing the entanglement entropy of the region R, we can study the time evolution of the entropy of the radiation. And the result is that at late times, it reproduces the Hawking's calculation, and it just keeps going up as time evolves. And the remarkable thing they found is that the entropy of the radiation should obey the so-called island rule rather than naive computation of the entropy of the region R. What the island rule tells us is that the region, so-called island here, appears inside the black hole interior, and the radiation starts to share the information of the island region at page time. As a result, entropy obeys the following formula, which is called island formula. The island formula tells us that the correct entropy of the Hawking radiation should be computed by a sum of the area term of the edge of the island and the matter entanglement entropy for the region R union the island I. And we extremize it over the all possible positions of the island in the bulk. The edge of the island, which is determined by the extremization procedure, is called quantum extreme surface, or QES in short. If you compute the entropy of the radiation according to this island formula, you can find the entropy start to decrease at the page time because the non-trivial island start to appear in the black hole, and the degrees of freedom of the island is shared by the Hawking radiation. So it obeys the unitary page curve. Another remarkable thing people found recently, the island formula can be derived by applying so-called replica trick, which computes the entanglement entropy by the method of the Euclidean path integral to this gravitational system. Replica trick allows us to compute the final entropy by using a trace law R to the n, where rho R is a reduced density matrix for the region R. In the usual replica trick, trace law R to the n can be computed by Euclidean path integral over n copies of the original geometry. In this case, we draw a picture of two copies of the original geometry. However, if the gravity is dynamical, such as in our system, we also have a wormhole solution, which connects each copy of replica sheets. Such wormholes are called replica wormhole, and this dynamically created wormhole corresponds to the dynamical emergence of the island region in the gravity system, and we can reproduce the island formula. Okay, so this derivation using replica tricks is good, but at the same time, it is somewhat formal and limited. This is because it relies on the Euclidean path integral method, so it's not clear whether it can apply to evaporating black holes where there's actual information loss as well. So the main goal of this talk is to derive the island formula for black holes that form by collapse and then evaporate by using the gravitational path integral. Okay, let me briefly explain the plan of today's talk. For part one, I'd like to talk about the background geometry. If we put it in a replica number, we study n equals 1 geometry. As I already explained, the replica method only applies to the state created by Euclidean path integral. So I'll explain how to construct an evaporating black hole by using Euclidean path integral in this section. For part two, we apply the replica method to compute the entropy of the Hawking radiation to the evaporating black hole background explained in part one. And we derive the QES condition in the island formula from the Einstein equation for the replica wormhole. Okay, so let us start from part one about the background geometry. The basic question here is how to apply the gravitational path integral to an evaporating black hole. The paper by AEMM constructed an evaporating black hole by joining quench. Joining the gravitational region and the flat path region at a certain time here creates the shock waves, which play a role of gravitationally collapsing matter. But if we try to apply the path integral method to this geometry, one can find the following problems. First, the Lorentzian spacetime in this setup has no time reflection symmetry. which implies that the geometry has no real Euclidean continuation. The second, as I will explain in detail, gluing a gravity to the flat region in the Euclidean signature is highly non-local due to the so-called conformal welding problem. And the conformal welding problem is generically hard to solve. We constructed an evaporating black hole background from the Euclidean path integral, which overcomes these two difficulties. Okay, let me explain about that. The starting point of the constructing our evaporating black hole background is an eternal ADS black hole coupled to a bus system, which doesn't evaporate at all. We consider the two-dimensional gravity, so-called JT gravity, living in ADS2 spacetime, and couple it to the two-dimensional CFT. We also have a vast region where the same CFT lives, but there's no gravity. As it is known well, in the JT gravity, bulk degrees of freedom reduces to the degrees of freedom how to embed the ADS boundary to the bulk. Here, this is the ADS boundary. And this degrees of freedom is represented by the map x of t between the ADS to coordinate x and the time on the boundary t. In our case, the physical time t can be interpreted as the time coordinate of the vast region. We glue the gravity and the vast region by using this dynamical degrees of freedom on the boundary x and t. If we couple an eternal black hole in ADS to the vast system at the same temperature, the geometry isn't backreacted at all. So the eternal black hole in ADS is still a solution even after coupling to the bath. This eternal black hole is nothing but the Hartree-Hawking state in the ADS2 coupled to flat system. So we can create a state by performing the Euclidean path integral over the Euclidean geometry I draw here from Euclidean time minus beta over 2, where beta is the inverse temperature of the system, to the time 0. This is the eternal black hole, which is thermal equilibrium with the vast system and doesn't evaporate at all. To break the equilibrium and let the black hole evaporate, we insert a primary operator during the performing the Euclidean path integral near t equals 0, as I draw in this picture. As I argued in the literature, this type of the insertion of operator in the Euclidean regime creates the shockwave in the Lorentzian geometry like this. And one of the shockwave is sent to the gravity region and increases the temperature of the black hole. And as a result, we can break the thermal equilibrium and the Hawking radiation can escape into the vast region and the black hole evaporates. In this case, we will have a non-trivial solution for the gluing function x of t, and we want to get it as a solution of the Einstein equation for the gluing function. So in order to write down the Einstein equation, we have to know about the matter stress tensor in this gravity class path system. So let me briefly explain how to compute the stress tensor in this glued system. The main difficulty is that we have two different coordinate systems in the gravity region and the bus system, respectively. In order to compute the stress tensor, as we usually do in the CFT without gravity, we want to cover the entire region by a single coordinate system. For instance, one might consider to extend the flat space coordinate denoted by y into the gravity region by some non-holomorphic map f of y and y bar. But generically, resulting metric is not conformally flat like this. So we don't know how to compute the stress tensor in such a metric. Instead, we want to map each coordinate in gravity and the mass region by holomorphic maps F and G to a single coordinate system Z, which covers the entire system. Holomorphic maps F and G should match at the interface of the gravity and mass region as this one. And since the interface itself is determined by the gluing function x of t, so the maps F and G is no longer depends on the gluing function through this matching condition. The problem how to give a holomorphic maps F and G for a given gluing function is called the conformal welding problem. And it's generically hard to solve. However, once we found a gluing map F, since the metric of the covering coordinate Z is conformally flat, we can compute the CFT stress tensor by usual transformation rule of the stress tensor in CFT. I will not explain in detail, but in our paper, we found a non-trivial solution of the conformal welding problem in the case of our setup I explained. And our solution exists only on the Schwinger-Kellich contour like this, not on the Euclidean section of it, which represents the evaporating black hole. This is consistent with the fact that the evaporating black hole solution is a solution in the Lorentz region rather than the Euclidean signature. Remarkably, stress tensor computed the outgoing stress tensor computed by the solution of the conformal welding problem represents the flux of the Hawking radiation. So here, the stress tensor of the Hawking radiation automatically derived by the solving the conformal welding problem. And while generically welding map no longer depends on the gluing function, as I explained, but our solution gives a totally local equation of stress tensor and the equation of motion for gluing function. And the equation of motion for the gluing function can be written as this. This is the equation for the Schwarzschild derivative of the gluing function, and which we can solve easily. So the mass of the black hole computed from the solution behaves as this plot. So once the shockwave from the flat region is injected into the gravity region, mass of the black hole increases by the energy of the shockwave, as Hawking radiation escapes into the flat region, black hole evaporates, and the black hole mass decays until black hole is fully evaporated. Okay. So now we created an evaporating black hole by Euclidean path integral method. So now we are ready to talk about its replica geometry. We compute the entropy of the radiation by taking the interval on the right flat region here, plus the entire left system. The usual computation of the entropy of the region R gives us the eternal growing behavior like this. And if we compute the entropy by using the island formula, when the entropy of the radiation becomes enough big, a non-trivial island appears inside the black hole, and the entropy starts decreasing like this. The idea of the replica wormhole is that if we try to compute the entropy of the radiation by using a Euclidean path integral, we have two different contributions. We have different contributions from a different replica geometry representing trace low r to the n. Here I draw two main contributions in the case of the replica number 2. The left geometry gives the usual Hawking's calculation of the radiation, the entropy of the radiation, which glows forever. On the other hand, on the right, I draw a wormhole contribution, which connects the two different replica sheets with each other. And this corresponds to the situation where there is a non-trivial island in the block. This wormhole can be represented by a dynamically created branch card here on a single sheet. Using the time left, I will explain briefly how this replica wormhole solution actually gives the island computation. The replica wormhole is the solution of the glowing function xn of t defined on the Schrödinger-Keldysh contour on the replica sheet. In this sheet, we have a fixed branch cut corresponding to the region R in the box region. And additionally, we also have a dynamical branch cut representing replica wormhole geometry. The position of branch cut A is dynamically determined by the Einstein equation I will explain. The Einstein equation for the replica wormhole is formally written down as this one. On the left, we have a geometrical part of the Einstein equation. In addition to the usual Schwarzschild derivative part of the glowing function xn of t, we also have additional contribution represented by R, which comes from the back reaction due to the existence of the dynamical twist effect at A in the gravity region. This contribution is necessary for the entire geometry to represent a smooth replica wormhole geometry. On the right, we have a stress tensor on the replica wormhole. In order to get the stress tensor, we again have to solve the conformal welding problem for the replica number n greater than 1. But details of this solution is not important to get a position of the twist defect A. The stress tensor is given by the sum of the background contribution here, plus additional contributions from twist operators at A and B, and the stress and also stress tensor coming from the welding. To get the position for the twist defect A, let us focus on the singularity at the position of A at the edge of the dynamical branch cut. Since we can find that the Schwarzschild derivative term and the welding stress tensor term is regular at the position of A, so we should look at the residue of the R term and the stress tensor coming from the twist operators. As Lukowitz-Maldacena argued, in general, the R term associated to the back reaction of the twist defect gives us the derivative of the area term at the position of A. And in our paper, we checked it by using the expressed form of the R term and the area term. And moreover, the stress tensor of the twist defect is related to the derivative of the replica partition function of the matter by conformal world identity. And the replica partition function of the matter gives us the matter entanglement entropy for the region I union R in this case. So the Einstein equation gives us the condition for the position of A written as this one. But this is nothing but the extremizing condition for the island formula. So we briefly saw that the replica wormhole in an evaporating black hole actually gives us the island formula. So this is a summary. I will not explain in detail, and I will stop my talk here. Thank you.
Thank you very much. Are there any questions? So can I ask one question?
Okay.
So in the second part, so you talked about so derivation of QS condition. But so did you use some Lorentzian nature of your setup here?
Yes, yeah. I think it's formally same in the Lorentzian signature, and and the Euclidean signature. But when we pick the residue of this combination, we consider the Schrödinger-Kellich contour, then get the condition for the QES. But this is essentially the same as the argument in the Euclidean signature and the Lorentzian, whether the Lorentzian or Euclidean is not so important in this case.
So does it also work for multiple interval cases? I mean, so if iron consists of several intervals.
Yeah, I think so. If we have a multiple interval in the flat region, this can apply to such a more general cases. But yeah, but I'm not sure for the case where there is a dynamical branch cut, several multiple dynamical branch cut in the gravity region. I'm not sure whether it can be generalized to this type of case. Yeah.
Okay, thank you. I think Tomonori has a question, so please go ahead.
Yeah, I have a question. So is it possible to put the operator on this, I mean, Euclidean part of the geometry or the bulk part to get this?
So you mean you want to put an operator in
right,
the
instead of
gravity...
putting it to the bath, but I just want to put it on the bulk region or Euclidean, region which prepares this black hole.
Yeah, I haven't considered that, but I think the main difficulty in that case is, again, to solve the conformal welding problem, I expect. Let me see. Yeah, the reason why we can solve the conformal welding is that in the case where we insert an operator on the bath region, the only ingoing stress tensor is coming from the shockwave created by the operator. This is essential for solving the conformal welding problem in our case. But if you insert operators in the bulk region, we have ingoing stress tensor and the outgoing stress tensor as well. So we cannot apply our solution of the conformal welding problem in this case. So we have to resolve the problem in this case. So I don't know how to solve in general this case. So yeah.
Do you think that you can solve it in leading order in this high temperature limit?
The leading order of high temperature limit, I think the leading, so perturbative solution of the conformal welding is well known, and we can write down the explicit form of the solution. So at the leading order of the the leading order of the high temperature limit, we can write down solution. But I'm not sure whether it represents interesting evaporating black hole solution or not, because at the leading order, the energy excitation by the insertion of the operator is very small, and I'm not sure whether we can see the interesting phenomena from such case.
I see. Thank you.
Okay, so Jisha has a question, so please go ahead.
Thank you. Thank you very much for the wonderful talk. I have a very naive question. So if you consider an initial state with the 0 temperature, and then insert some excitation with the operator, can you interpret that as an evaporating black hole?
Sorry, you want? So here start with from the finite temperature black hole and inserting operators to create the evaporating black hole. But your question is about
yes, start from the zero temperature.
Zero
say start
temperature.
from, yeah.
And sorry, can you say again what is your question?
Sorry. So if we start from an initial stage with zero temperature, and then insert some excitation with the local operator, like what you did for this setup, can we again interpret that as some evaporating black hole?
Yeah. Actually, Actually, we started from the finite temperature and inserting operator to create the evaporating black hole. But after we solved the conformal welding problem and write down the equation of motion for the like this, like this, then we can take a limit. Beta goes to 0. Beta is the background black hole temperature, and then I think we can get the evaporating black hole created by a local operator on the zero temperature black hole.
I see. Thank you very much.
Yeah.
So any other question? So if not, let the sun speak again. And so this is the end of the afternoon session, but there is an announcement about the coffee break from the organizer. So Tomonori, so do you have an announcement?
Yes. Okay. So we in this conference we use this limo for the coffee break and social interactions. And okay, I sent a link. I put a link to this chat, so you can just use it to log into limo. And okay, so originally we planned to have to open this the limo for the coffee break in this in the afternoon 5 p.m. to 10 p.m. But in the end, we decided to open it also lunchtime. And I have sent a link to all of you. I mean, in one of the emails today, and so you can just use it to link. And also for speakers, please make sure to send the slides so that I can put it on the website. Yeah, that's it. Thank you.
Thank you. Okay, so this is the end of the session. Okay. So
okay, yeah, thank you very much. So let me close this session.